This tutorial describes molecular dynamics playback. Molecular dynamics can be run at real time when you watch the trajectory as it's being computed, or at playback time when you watch the trajectory at a much faster rate, at the rate that it comes off the disk. This is particularly useful when the computing of the trajectory is a long, involved process. So, for example, if one was doing ab initio calculations on a big basis set, this would take a long time, and you don't want to try and attempt to watch the trajectory as it's being computed. You compute it overnight and store it, and then you play it back at a rapid rate and do averaging and various things at playback time. And this illustrates the creation of trajectories for playback. So we have here a couple molecules, and supposing we wanted to look at a collision between these two, what we might do is go up and choose an ab initio method, say a 631G single star basis set or something like that. Go up and turn on molecular dynamics and tell it to do, supposing we want to do a picosecond or something at a smaller step size, and we want to do 300 degrees Kelvin and so on, and do this trajectory. Well, we could go ahead and do it, and it's got 80 basis functions and so on and so forth, and this trajectory will be computed in a relevant, in an appropriate fashion. Here's now the first step on this trajectory, and it just is so slow that we can't really watch it in real time, but we can compute this overnight or whatever, and so I'm going to show you how to store that trajectory and then play it back. So we're going to cancel this, and instead of trying to compute this, what we're going to do is look at playback time. And rather than do this one and compute this for however long it takes, I'm going to speed this up so that we can see what's going on here in real time. So we're going to do an mm plus calculation, make this go much faster, and we're going to do molecular dynamics, and let's actually do 1/10 of a picosecond. Let's go back to longer, bigger step size, and when we want to do playback, what we have to do is have to create a snapshot. Now, a snapshot has a name. So, for example, snapshot.hin is a hin file which will contain a pointer to the snapshot file. The snapshot file is a separate file containing the trajectory, but hin files contain a record that is a pointer to the snapshot. So what we're going to do is put that record into this hin file, or create a hin file with a snapshot record in it, and I'm going to call that hin file snapshot. It's really a molecule, a hin file with a pointer to a snapshot. So I've already got one out there, so it's to replace that, and basically away we go. And so this is going relatively quickly now. This trajectory is an inelastic one. It's only molecular mechanics, so they don't react, and they just bounced off each other, and we did the 1/10 of a picosecond very, very quickly. And in that process, it saved a hin file called snapshot.hin, and in that hin file is a pointer to a trajectory file, snapshot file, SNP file. So we're finished now with that. We can do new or go off and do some other separate calculation and so on. And if we ever come back and we open this snapshot.hin file, it tells us that this system has a pointer to a trajectory in it, so that because that trajectory refers to a particular molecular system, if we change the molecular system, we'll lose the snapshot. So we shouldn't do that. So anyway, so here's the system, and it has associated with the trajectory that we've already computed. And if we go up to molecular dynamics and ask for playback, then we can do so. If we take a look at this now, it tells us about the snapshot file. It's stored here in this particular trajectory, which happened to be the current trajectory, a snapshot file that the hin file points to, and this is 100 steps at 0.001 picoseconds, and we can look at this either from the whole trajectory or a piece of that trajectory. We can set these start and ending times if we want to look at the trajectory. So if we just look at it, away we go, and it was so fast that it really couldn't see it. It took place so quickly. Anyway, so that's the playback. And whoops. So here is the snapshot, and if we want to, we could create a movie out of this. In the same directory, we could create a file called dynamics.avi, and this will be a little bit slower now. And when we make this movie, we have to tell it what kind of codec we want to use, and we'll use this one here, and go ahead. And this is slower, but we now have an AVI file, which is a movie file that we can use to show this as well. The playback is actually much faster than the movie. There's one other facet about playback that's important, and that is that when you playback, it is possible to run a script at every step of the playback. If you have a special file stored in the program directory called chem-dynamics.scr, a script file, it will run this script at every step of the dynamics. And so, for example, if you wanted to show the orbitals during a chemical reaction, one could, at every step of the playback, actually calculate the wave function and show that continuously as you were playing back the trajectory, showing the orbitals being distorted and so on as the collision took place and so forth. So those are various facets of playback, which is quite different from the real-time trajectories that one sometimes looks at.